Hello, Year 11 Chemistry. This is hopefully the last of the videos for your assessment task, and this video is to guide you through the last 2 pages of your assessment, the last 2 pages of Part 2B, all about chemical equations. And the first of those last 2 pages is to show you why chemists use chemical equations, because in a simple chemical equation, a lot of complicated information is contained. So we're going to do 2 activities here, one converting a paragraph of text into a chemical equation, and one of converting a chemical equation into a paragraph of text. So the first equation we've got here is this equation here, or this paragraph here, about the reaction of gaseous phosphorus pentachloride. And so as I was doing this, the first thing I want to do is make sure I know what chemicals I've got to put in my equation. So the key information here is I've got 2 molecules of gaseous phosphorus pentachloride, each containing 1 phosphorus and 5 chlorine atoms. That's the first chemical I'm dealing with. Then it says that decomposes to produce 2 molecules of gaseous phosphorus dichloride, each containing 1 phosphorus and 2 chlorine atoms. And last but not least, I'm told I also produce 3 molecules of diatomic chlorine gas. So there's 3 chemicals in my equation, and I've got to condense that information into one chemical equation. So let's look at the first one. I've got 2 molecules. 2 molecules means I put a 2 at the front. I've got 2 molecules of gaseous phosphorus pentachloride. Now, straight from the name, we should know what the formula is, but this paragraph's got all the information. So it says each containing 1 phosphorus and 5 chlorine atoms. So the formula of the compound is PCl5, but I've got 2 of those phosphorus pentachlorides. And it's also a gas, so I've got to indicate it's a gas in there. So that little statement there, 2 PLC5 gas, tells me just as much information as that 2 lines of text there, pretty much. And it says it decomposes, so that means it's going to break down and to form new chemicals. The first of those 2 chemicals is 2 molecules of gaseous phosphorus dichloride. So 2 molecules of phosphorus dichloride. It tells us each contains 1 phosphorus and 2 chlorine atoms, but we know that from the name anyway, and it's a gas. Plus 3 molecules of diatomic, we know that means 2, chlorine gas. And there we've converted that 3 lines of text into one very short line of a chemical equation. It's good practice though to make sure things are balanced. Let's just double check this equation is balanced. To be balanced, the atoms in the reactants must be the same as the atoms in the products. So let's see. We've got 2 molecules of this PCl5, which means we've got actually 2 phosphorus atoms and 2 lots of 5 chlorine atoms, which means we've got 2 phosphoruses in total and 10 chlorines in total. And that should be the same as in our products. So here we've got 2 lots of phosphorus and 2 lots of 2 chlorines. So here we've got 2 phosphoruses and 4 chlorines. And here we've got 3 lots of 2 chlorines, which makes 6 chlorines. So in total, we've got 2 phosphorus and 10 chlorines. The reaction balances. This next one here, I don't think this is so much fun. We've got to convert a nice, succinct chemical equation into a paragraph of text. This is to once and for all show you that chemical equations are useful and that we won't do any more of this ever again because it's so horrible converting a chemical equation into text. First of all though, these should all be gases, so I'll put little g's underneath all these. And we should know the name of some of these chemicals, but some we don't. For the record, I've given you a bit of a clue. C2F6 is called hexafluoroethane and CF4 is called tetrafluoromethane. I wouldn't expect you to know the name of those chemicals. So how are we going to convert this into text? We need to say for each of these 4 species in our reaction how many there are, what atoms are in the molecule, and what state it is. So let's give that a go. I'm not going to write it out because that would be horrible for all of us. Let's just see if we can say it out loud and just imagine how long this paragraph would be. We'd have to say that 3 molecules of hexafluoroethane, each containing 2 carbons and 6 fluorines in the gaseous form, reacts with 2 gaseous molecules of this compound is called nitrogen trifluoride, each of which contains 1 nitrogen and 3 fluorine atoms, and they react to produce 6 gaseous molecules of tetrafluoromethane, each containing 1 carbon and 4 fluorine atoms, and 1 molecule of gaseous diatomic nitrogen. A lot of information is packed into that one little chemical equation, which is why we use chemical equations. But for your assessment task, you've got to convert, I think it's 2 equations into paragraphs of text. The next skill we're looking at is a very important skill for chemistry. That's balancing chemical equations. We just said previously that in a chemical equation, the atoms in the reactants must equal the atoms in the products. So the atoms here, atoms in reactants, must equal the atoms in the products. And the reason for that is something to do with the law of conservation of mass, or the law of conservation of atoms. You cannot create or destroy atoms, you can only rearrange them, and therefore the same number of atoms must be on both sides of the equation. So how are we going to go about balancing this equation? There is no strict rule, or there's none that I've seen anyway, that go through exactly how to balance an equation. It's a bit of an art and a skill at the same time, but there's a few tips you can pick up along the way. And the first of them is I always find it useful to balance the metals first. If your metals balance first, then you've got to balance something else. So in this equation, looking at our reactant side, we have Na2. That means we've got 2 sodiums here, but we only have 1 sodium on our product side. Now, it's tempting to just change the formula of sodium chloride, Na2Cl, and that solves my balancing sodium problem. But that is 100% absolutely wrong. We just spent a week or so learning about why the formula of molecules is the way they are, or why the formula of compounds is the way they are. That's because 1 sodium loses 1 electron, 1 chlorine gains 1 electron. They both get a charge of +1 and -1 respectively, and they bond together. 2 sodiums will not bond with 1 chlorine, so we can't just willy-nilly change the formula of sodium chloride. But what we can do is change how many sodium chlorides we make. So what it's okay to do is actually say we have to make 2 sodium chlorides. Because I've got 2 sodiums in the reactants, there must be 2 sodium chlorides in the product. So now we've gone and balanced the metals. The next thing I like to do is balance the polyatomic ions. And this is sometimes useful, but doesn't always work. To balance polyatomic ions, you've got to make sure the polyatomic ion appears on both sides of the equation. And if you look here, we have 1 carbonate here, which is nice, but carbonate doesn't actually appear anywhere on this side. We do have carbon dioxide, but that's not carbonate. So unfortunately for this reaction, we can't balance the polyatomic ions. We have to balance something else. If I've already looked at my metals and my polyatomic ions, the next thing I usually look at is my most complicated species, or one of my non-metals. I usually leave things like hydrogen, oxygen, and carbon to last. So in this case, chlorine will be the next thing I'll balance. If I look at my reactants, I've currently got 1 chlorine here. I used to have 1 chlorine here too, but I've decided to put my 2 sodium chlorides there, so now I've actually got 2 sodium chlorides here. Like before, I can't put a 2 next to the chlorine here. I can't change the formula of hydrogen chloride, but I can say I've got 2 HCl molecules. And that means I've now got 2 chlorines here and 2 chlorines here to go with my 2 sodiums here and my 2 sodiums there. So we're getting close to this hopefully being balanced. Let's check some more things. We've checked the metals, we've checked the polyatomic ions, we've got carbon, hydrogen, oxygen left, and anytime you've got carbon, hydrogen, oxygen in an equation, it always seems to work best if you balance them in that order, CHO. I can't think of a saying to go with that apart from just CHO, but that's the way I balance things. So let's check our carbons. In this compound here, we have 1 carbon. We've also got 1 carbon in carbon dioxide, so our carbons are balanced already. Don't have to change our carbons. Next, look at our hydrogens. No hydrogen in sodium carbonate. We do though now have 2 hydrogens here. Where's hydrogen on this side of the equation? We've got 2 hydrogens here, so hydrogen is balanced. The last thing is oxygen. We currently have 3 oxygens here. We have 1 oxygen here. We have 2 oxygens here, so our oxygens are balanced as well. So all we need to do to balance this equation was add a 2 in front of the HCl and a 2 in front of the sodium chloride, which tells us that 1 unit of sodium carbonate reacts with 2 units of hydrochloric acid to produce 2 units of sodium chloride, 1 unit of water, and 1 unit of carbon dioxide. And just to introduce you to some new terminology we're going to encounter soon, that means that 1 mole of sodium carbonate will react with 2 moles of hydrochloric acid to produce 2 moles of sodium chloride, 1 mole of water, and 1 mole of carbon dioxide. So that's the order in which I'll balance metals, polyatomic ions, complicated species, leaving carbon, hydrogen, oxygen till the very end. Let's look at this next equation now. This is one of the more famous Year 11 balancing equations because it's a little bit complicated. It looks so simple, but it's got a bit of complexity about it. And let's see if we can do the same order of balancing we did before. We start off with our metals. Our metal's aluminium. Look at aluminium here. I've got 1 aluminium and 1 aluminium, so that seems balanced. Good. Polyatomic ions. No, I've got no polyatomic ions, but I do have chlorines. Let's balance our chlorines. I've got 1 chlorine here, but I've suddenly got 3 chlorines here. That's a bit of a problem. I need to balance that. I can't change the formula of aluminium chloride. I'm not allowed to get rid of that 3. That's the formula of aluminium chloride. And I can't just put a 3 here. I can't change the formula of hydrogen chloride. But what I can do is include 3 hydrogen chloride molecules. So now I've actually got my 3 chlorines and my 3 chlorines. So my chlorines are balanced. Now we can come to our hydrogen. Let's have a look at hydrogen. I've currently got 3 hydrogens here, but I've got 2 hydrogens here. That's a problem. What can we do? There's 2 ways of solving this problem. One a bit sneaky and a bit simple, and one a little bit trickier. What can we do to make sure we've got 3 hydrogens on both sides? The first way, and the most common way you'll see, is if you can't put the same on both sides, you find the lowest common multiple of both. So I want to turn this into 6 hydrogens and this into 6 hydrogens. How do I convert this into 6 hydrogens? I'll actually need 6 hydrochloric acid molecules. And how do I make this into 6 hydrogens? I'll need 3H2. Only problem is, now I've changed this to 6, that means my chlorines won't be balanced anymore. So let's go back to our chlorines now. Our chlorines, I used to have 3, but now I've got 6 chlorines here. I've only got 3 chlorines here. I'm going to make 6. That's got to be a 2 out the front now. So now I've got 6 chlorines here. But that's going to stuff up my aluminium balancing, because now I've got 2 aluminiums here, which means I need to put 2 aluminiums out the front. So 2 aluminiums react with 6 HCl's to produce 2 AlCl3 plus 3H2, or 2 moles of aluminium react with 6 moles of hydrochloric acid to produce 2 moles of aluminium chloride, or 3 moles of H2. However, there was a slightly sneaky shortcut we could have taken, and it's to do with diatomic molecules. And sometimes this will make your life a whole lot easier when you're balancing equations. Let's start from scratch again. We've got aluminium, 1 aluminium, and 1 aluminium. So far, aluminium is looking good. We balance the chlorine. We need to add 3 chlorines, because we've got 3 chlorines here. We wanted to have 3 chlorines here. We put a 3 out the front. The problem arose is when we had 3 hydrogens here, we only had 2 hydrogens here. What we can do though, because this is a diatomic hydrogen molecule, we can put fractions in front of it. And if I want to turn 2 hydrogens into 3 hydrogens, if I put 3 on 2 at the front times 2, that gives me my 3 hydrogens. So I'm going to convert that to 3 on 2. So that's another way of doing these equations. We can say that 1 mole of aluminium reacts with 3 moles of hydrochloric acid to produce 1 mole of aluminium chloride and 3 on 2 moles of hydrogen gas. That's quite a challenging problem, that one there. We'll do some more like that later in the term. On to the next activity. Now we've got to convert a written reaction into a balanced chemical equation, and this involves a few skills. It involves getting the formulas right first, as well as balancing it. It's so important you get your formula of your molecules right, or your compounds right first, before you try and balance. Let's see what we can do. This says lead 2 nitrate reacts with potassium iodide solution, which means the state of solutions means dissolved in water. So the state is AQ, it's aqueous. It's not solid, liquid or gas, it's AQ for aqueous, which means dissolved in water. So those 2 solutions react to form potassium iodide and a precipitate of lead 2 iodide. Obviously that can't happen, that should be potassium nitrate. How silly. Anyway, so that's our chemical reaction. We need to write that down. First thing, what's the formula of lead 2 nitrate? You actually need to get out your cross method and figure out the formula before you start. It tells us it's lead 2, so it's lead 2 plus. Nitrate is 1 minus. I cross them over. I get PbNO3 2. I have to put brackets around there, so that's the formula of lead nitrate. So I'll write that neatly now. PbNO3 2. That's the first of my species, and I told you it was a solution, so you've got to indicate that it's aqueous. The next chemical, potassium iodide. Well, potassium is in group 1, it's got a valency of +1. Iodine is group 7, it's got a valency of -1. Cross them over, I'm just going to end it with Ki. So plus Ki, and once again, that's aqueous. The next thing, potassium nitrate. Potassium's valency is +1, nitrates is -1. I cross them over, I just get 1 and 1. So that's going to turn into KNO3, aqueous. And the last one, lead 2 iodide. Pb is 2 plus, iodine is 1 minus. Cross them over, we get PbI2. And they told us this was a precipitate, and that means it's a solid, a little solid's formed. So that's the first stage. It's actually probably the most important stage is that first stage, getting the actual formulas of all your species correct. Because now you've got the formulas correct, you can go ahead and balance. Just like before, let's balance our metals 1 lead, 1 lead. Lead is balanced. Next thing is polyatomic ions. I have 2 nitrates here. I need to get 2 nitrates over here. If I put a 2 out the front, I now have my 2 nitrates. The next thing is complicated species. I could have balanced potassium as well, I suppose, seeing it's a metal. Let's have a look. I've got 2 potassiums here. I've only got 1 here. I need to put a 2 at the front there. Iodines, 2 iodines here. I've got 2 iodines here. That's the balanced equation. 1 mole of lead nitrate reacts with 2 moles of potassium iodide to produce 2 moles of potassium nitrate and 1 mole of solid lead iodide.